conservation of energy in space, aka Kepler's laws, done Newtonian fashion. Let's take a look at potential energy of a satellite in orbit around something. There it goes. On Earth, we used mgh to measure potential energy, where h was our height above some surface somewhere. Could be the third floor, could be the second floor, could be the ground, could be underground. Hey, let's measure h from underground this time. Let's measure h from the center of mass. So from the center of mass all the way out to here, bless my soul, that's the variable we called r. Now g, we used to say was 9.81, but that's just because we live narrow little lives on the Earth's surface. Now we've found out that g, the acceleration due to gravity and the strength of the gravitational field, is actually equal to big G, the universal gravitational constant, capital M, the mass of the planet, divided by r squared. Oh, multiply by r, one of the masses cancel out, and we have gravitational potential energy in space, GMM, there's the other m, over r. True confessions, this is actually a bit of a hand-waving argument. The real formula for gravitational potential energy in space comes with calculus, and it's negative GMM over r. The negative makes sure that negative 1/10 is actually more than negative 1/5. That way it's closer to 0, and closer to 0 is technically more. That means that as far as magnitudes go, we can still use the idea of room to fall. So, where in orbit do you find the most potential energy? Here? Here? Somewhere in between? Well, if we're just looking at potential energy as the idea of room to fall, we should be able to eyeball the correct answer with or without the formula in the calculus. Where in this orbit do you have most room to fall? Well, you have most room to fall when you're furthest from the planet. Over here. Done. Closest to the planet, over here, we've got least room to fall. And that should make potential energy at a minimum. There, that wasn't so bad. What about kinetic energy? Where do you find the most and the least kinetic energy? Well, let's take a look at potential energy. If potential energy is at a maximum, you've used most of your energy, and you'll have very little left for kinetic energy. If potential energy is at a minimum, then you'll have lots of kinetic energy. What does this look like? Well, in a very extreme and badly animated PowerPoint clip, it means that when you're close to the planet, you'll move faster through having less potential energy, and when you're further away from the planet, you'll move slower through having more potential energy. This was what we saw in the Newton's mountain animation yesterday that was much more accurately done. Now, let's get out of orbit, if indeed we want to. We've been going round and round and round, faster when we're closer to the planet, slower proportionally when we're further away from the planet. Now we want to leave. Where does the energy come from? Well, at the moment, the energy comes from the chemical potential energy in our fuel as being burned by our thrusters. Fuel is expensive. If we run out, then we are going to be the Martian, eating Mars potatoes and counting down our remaining days of life very quickly. Why waste your energy? Fuel is expensive, and if we run out, we will be in trouble. So, whom do you want to do the work of breaking out of orbit? A, you, or B, somebody else, of which gravity is probably going to be the chief culprit. I'm going with somebody else. Gravity works for free. In order for gravity to do some of the work for you, the force vectors for force and displacement must be A, parallel, B, perpendicular. Yeah, I know, first semester physics. Gravity, work is dot product. Let's see, what were those Schuyler sisters singing about? The greatest vectors in the world? That's right, the greatest vectors in the world are parallel. Well, where do you find parallel force and displacement in an orbit? Let's look and see. How about at the perigee? Up here. Perigee is where you are closest to the surface of the planet. Force. Ooh, gravity is a centripetal force, and it goes toward the center of the planet. Which way are you going? You're going that way. That'll be your displacement, at least for the moment. And the vectors are perpendicular. They will do no work whatsoever. That means all the work to break out of orbit has to come from you and your thrusters. That's going to be expensive. Let's not go there. How about the apogee? The apogee is the point furthest from the Earth's surface. Well, there's gravity again going toward the center. There's the way you're going. And again, the vectors are perpendicular, and the force of gravity will do no work for you and save you no money and no fuel. Bummer! How about somewhere else? Here? Here? Let's do this pictorially. Perpendicular. Oh, this is worse. This is an obtuse angle. This is worse than perpendicular. It's negative 4. Oh, there we go. Acute, more acute, more acute, less acute, less acute, and we're back to perpendicular again. All right, we never did get parallel, but this is a whole Farsight closer to 0 degrees than any of those 100+ monsters we got over here. Gravity will do a small amount of work to break us out of orbit. Gravity will swing us around in the direction we already want to be going. So this is the smallest angle we have. This is going to be the most effective place to break out of orbit. Gravity will do some small amount of work. We want cosine theta to be as close as possible to 1, namely the angle as small as possible. So if you're on the inbound trip from the apogee back to the perigee at a certain location based on the size of your planet and the contours of your orbit, this is going to be a good place when you get there to fire those thrusters for a certain amount of time to get you the necessary change in velocity until you've achieved escape speed.